In Cycle 1, Lesson 6, we're going to move on from polynomial functions for the time being and start looking at what's called rational functions. Again, with the idea in mind that we're going to be really focused on the graphs using Desmos where necessary to help us understand what's called a rational function. Sometimes we're going to refer to it as a reciprocal function as well. Okay? So here's what you need to know. Think about what you know about a rational, the word rational numbers. Rational numbers are numbers that can be written as fractions. A rational function is a function that's written as a fraction. So to back up to what's written here, when you add, subtract, or multiply two polynomial functions, the result's just another polynomial function. And we're going to look at that later, so we don't have to get into that now. But you just have to know, there's four basic operations: add, subtract, multiply, divide, right? If you add, subtract, or multiply, you're just going to get another polynomial if you combine two of them. But that's not the case when you divide. When you divide polynomial functions, you're going to have one polynomial function on top of another polynomial function. So p at x on the screen here is a polynomial function. It could be a linear or a quadratic or a cubic. And q at x is another polynomial function, linear, quadratic, cubic, whatever degree. So that's the basic idea. But we know that we can't divide by zero, right? We know that in math it's not defined to divide by zero. There is no answer for dividing something by zero. So that's where this restriction comes in. So this is a restriction. You're probably a little familiar with restrictions from previous courses, and so we're going to be dealing with them again here. So what we have to keep in mind is that as long as the entire denominator doesn't equal zero, we're good. If something is going to make the denominator equal zero, then we've got a problem, and we have to identify that restriction. So let's look at the basic reciprocal of a linear function. So again, I talked about rational functions. That's one type of function where you have a polynomial over another polynomial. A reciprocal function is something that's related because it's definitely a fraction, but it's usually just going to have a 1 on the top or some constant number. So reciprocal just means flipping something upside down. So f at x equals 1 over x is the reciprocal of y equals x. If you just took that as a function, y equals x. If I talked about the reciprocal of that function, I'd flip the x upside down and have 1 over x. The reciprocal function of y equals x squared would be 1 over x squared. So that's where the term reciprocal comes from. And again, I'm going to use them both, and they're very much related to each other, but they're not exactly the same thing. Rational just means it's written as a fraction. So f at x equals 1 over x is both a reciprocal function and a rational function. Let's see what it looks like. So easy to make a table of values. For this, all we do is we plug in the x value into the equation. And so if I put negative 4 in for the first one, then I get negative 1 over 4. And I'm not going to worry about where I put the negative sign. Where I put the negative sign. I just stick it out front. So sticking in these different numbers, then I'd get, for this one, I'd get negative 1. So I'd get positive 1 over negative 1. But that's just going to equal, I'm going to simplify that down to negative 1. For this one, I'd get 1 over negative 0.5, which when I divide it out actually becomes negative 2, right? And then this one's going to be negative 4. And then this one's going to be undefined because I can't divide by 0. And then dividing by positive a quarter gets me 4, 2, 1, a half, a third, a quarter. All right, so let's graph these ordered pairs. And so we have negative 4. The scale is very hard to read. Let's see if I can at least darken it up a little bit. Alright, I'm going to have to guess that this is where the y-axis is, and this is where the x-axis is. That's a little easier to see. Alright, -4, -1, 1, 2, 3, 4, -4, -1/4. I think that's here. -3, -1/3, slightly lower down. -2, -1/2, slightly lower down again. -1, -1 here. -0.5, -2 is here. -1/3, -3, -1/4, -4. Alright, so we got these points here. Then when we get to an x value of 0, it's undefined. But then I start at +1/4 and +4, and so that picks up again about here, 1/3 3, 1/2 2, really having trouble reading this scale. Okay, let's say that one's there, 1/2, 1/3, 4. Okay, even if I didn't read the scale quite properly, you get the idea. You can see the shape. So if I connect these dots, imagine going farther out to the left. So imagine I went to -10, way out on the left side, and I stuck that in the equation. Well, -10, I'd have 1 over -10 as my y output. So I'm never actually going to get quite up to the x-axis here. I'm going to get closer and closer to the x-axis the farther left I go. And then as I move in towards the x-axis, as I get closer and closer, I'm going to end up with bigger and bigger negative numbers as I go. So the last one that I'm just connecting to here was -1/4, -4. But say I had -1/10. The y output would then be -10. So it's going to keep going down. It's going to go down very sharply, and I can't draw it well enough to do it justice. No human can. But what I want you to think about for this chunk I've just drawn is that as I go farther to the left, I'm going to get closer to the x-axis without ever touching it. As I move in farther to the right towards the y-axis, it's going to go down and down towards infinity. It's never actually going to touch the y-axis. And then it does the same type of thing up here on in the upper in quadrant 1. So if I'm started here, the way I'm drawing it, as I get closer to the y-axis, it's going to go up very steeply without ever actually touching it. As I go out this way, it's going to get closer to the x-axis without ever actually touching it. If my pencil touches the x-axis, then, you know, it's okay. I understand what it's supposed to look like. So there's my graph. It has what's called an asymptote here on the y-axis because it never touches the y-axis. It can't. It's undefined here, right? So where it's undefined, there's going to be what's called a vertical asymptote. So I've drawn that in red, and that just means that the graph will get closer and closer to this vertical asymptote without ever actually touching it. It also happens to have a horizontal asymptote because it doesn't touch this x-axis either. So those are asymptotes, lines that the graph gets closer to without touching. Describe what happens to the function as x approaches -infinity. So, in other words, what's happening as we go out this way? So imagine you're starting at the origin and moving that way. Well, as the x values are going closer and closer, getting bigger and bigger negative numbers, the y values are actually getting closer and closer to 0, aren't they? Y is approaching 0. And I'm going to put a little negative sign up there to show that it's approaching 0. It's getting closer to a y value of 0, and it's approaching from below. So that's what the negative sign means. What about as x approaches positive infinity? Let's pick a different color. So if I start at the origin and go this way, on the x-axis, what's happening to the y's? they're getting closer and closer to 0 again. However, they're coming down from above this time, so I'll put a plus sign there. What happens as x approaches 0 from the left? Let's go purple, all right? So as I go from the left, so I'm coming in from the left side of the graph towards the y-axis. Well, y values are approaching, they're going downward, they're going down very sharply, and so they're just getting bigger and bigger negative numbers. They're approaching negative infinity. And I've run out of different colors. Let's just go black then. So I come in from the right. Well, now the y values are going up, right? As I follow the x, the graph in on the x-axis from the right, the y values are getting bigger and bigger, and they're approaching positive infinity. Okay, so that's a reciprocal function. It's a type of rational function. That basic shape you want to be familiar with, and you may be already familiar with it. Okay, so let's look at another reciprocal function. This one is the reciprocal of some linear function. I guess it'd be the reciprocal of y equals 2x minus 3. And then we make it the reciprocal by putting 1 over top of it, or imagining it as a fraction already that we flip upside down. We want to know what this graph is going to look like. So graph the function on Desmos and then sketch the grid. Okay. Desmos. Y equals 1 divided by 2x minus 3. Desmos can handle pretty much anything that we want to throw at it. So 1 divided by 2x minus 3. So we can see, just from looking at this, it's got the same basic shape. It's got those two sections. What we talked about as an asymptote before is no longer on the y-axis. It looks like it's been shifted to the right. The horizontal asymptote that was on the x-axis still seems to be there, though. So where the vertical asymptote, this up and down asymptote, seems to be is it looks like it's at about 1.5, right? So if I were to draw a vertical line at 1.5, that actually looks pretty good as to where the vertical asymptote is. They're overlapping a bit because I've got it on projector mode, but you can see a bit better how they're not really, the red line isn't supposed to be touching that asymptote, which isn't even really there. It's just I put it in so you can get an idea of where it's supposed to be. So again, get our axes here. Again, I'll just have to make up my own because this scale is no good. So we saw the graph. It was that's a terrible axis I've drawn, isn't it? Well, I'm not going to mess with it now. It actually crossed the x-axis and it went about as far as 1.5, and then it went down like that. And maybe it'd be best to even get that vertical asymptote in there at about 1.5 is where it appeared, just so I have something to go by. And then we had the other section that was like this. That was the basic shape. Now, how did I know that the vertical asymptote was at 1.5? Well, I looked at it at the graph, but I kind of cheated as well. I did know that the vertical asymptote was going to be at 1.5. And the way I knew was because I thought back to this. Remember, we're going to have a vertical asymptote where the graph is undefined. Where is it undefined? It's undefined where 2x minus 3 equals 0. What value of x is going to make 2x minus 3 equal 0. Well, we could actually solve that little equation. And lo and behold, if x equals 1.5, then the denominator of this rational function equals 0, undefined. So that's why the asymptote is there. So the domain, then, is going to be, it goes on forever to the left and to the right. In fact, it can be anything. If you look at the equation, any x value is fine, except if x equals 1.5. So I could just say XER where x is not equal to 1.5. If I just want to restrict that one number, then that's fine. I can do that. The range is all real numbers. I'm going to start a bit farther over. Again, it hits everything except one place on that y-axis. There's never a point that is that's on the x-axis. So because the horizontal asymptote is there, we know it's never going to touch y equals 0. So those are the domain and range, and related to the domain and range are the vertical asymptote. If the graph can't equal 1.5, then we know the vertical asymptote is at 1.5. If the graph's never going to touch y equals 0, we know the horizontal asymptote is at y equals 0. So those two things are very much connected to each other. Describe the behavior of the function near the vertical asymptote. So we're going to go and do like we did above here, as x approaches negative infinity, as x approaches positive infinity, that type of thing. I guess it's not infinity in this case, so it's what's happening as x gets closer to 1.5. So as x approaches 1.5 from the left, I'm going to put a negative sign there. So in other words, as x comes from the negative side towards 1.5, what's happening? Well, the graph is taking a sharp turn downwards, isn't it? So y is going down towards negative infinity. As x approaches 1.5 from the right, from the positive side, y is swooping upwards can't quite delete that. Okay. It's swooping upwards anyway towards positive infinity. Then we have the end behavior. So the end behavior is what happens as x approaches, let's say, negative infinity first. So in other words, what's happening as we go from the middle of the graph out towards the left. And as you see that, you can see that the end behavior is that y is approaching 0, and it's approaching it from below. And as x approaches positive infinity, so as it goes out this way, y is also approaching 0, but it's approaching it from above. This is the more traditional and accepted way to do end behavior. When we were doing polynomial functions, we talked about quadrant 1 or quadrant 3 to quadrant 1 or quadrant 2 to quadrant 1. We can't really do that anymore for more difficult graphs like this one. So we have to use proper notation. This is the notation you have to get used to at this point. When k is less than 0 in f at x equals 1 over kx minus c, graph the function and draw a sketch of the grid. All right, so we're looking for a value where we have, I guess, a negative k value. So let's just start by graphing it and then see where we go from there. So we're graphing the function n at x equals 4 over 5 minus x. I'll just call it y equals 4 divided by 5 minus x. Okay, here's the graph. Same shape, it's been flipped around a little bit. It's got the two parts to it again. There's definitely a vertical asymptote going on. It appears to be at x equals 5. Can you predict, or can you explain why it seems to be at x equals 5? Clearly we can see on the graph that's where it is, but can you explain to yourself why that would be where the asymptote is? If you can't, pause it for a second, think about it, but here's the reason. It's because if x equals 5, look back at the equation. If x equals 5, then we have 5 minus 5 on the denominator. That should give us 0. Division by 0 is a problem. We also have a horizontal asymptote on the x-axis again. So let's sketch this quickly. So we had a vertical asymptote at 5. Let's just say that that's here for argument's sake. And so our graph looks something like this and this. It's two parts again. Now, this equation is a little bit in an unusual format. Normally, if I was to put it in a more traditional format, I'd put the x first. So I could rewrite it as 4 over negative x plus 5. And I could even factor out that negative 1. Then I'd have x minus 5 in brackets here. And this negative 1 here, I didn't write the 1 in, but it's negative 1 assumed to be here. That's our k value, our transformation. So that's what they're talking about, a k value less than 0. Remember what k does? K is our horizontal compression stretch. This has, make it a negative k value, has reflected things in the y-axis, which is why in the first two, we had those two sections of the graph sort of in the lower left and upper right. Lower left and upper right for the sections of the graph are. In this one, we got the upper left and lower right because the function has been reflected in the y-axis. Describe the behavior of the function near the vertical asymptote. All right, well, this time the vertical asymptote, as I pointed out, was 5. So as x approaches 5, from the, let's say, from the left, y is approaching positive infinity. Y is going up very quickly. As x approaches 5 from the right, y is approaching negative infinity. It's going down very quickly. The end behavior as x approaches negative infinity, so starting in the middle and going towards the left, y is getting closer and closer to 0 from above. As x approaches positive infinity from the center, going out to the right, y is getting closer and closer to 0, but from below. How would you describe the major changes in the original function when k is less than 0? Well, I already just described that. It's a reflection over or in the y-axis. It's a horizontal reflection. Last example, finding intercepts. Determine the x and y intercepts of this function here. So 2 over x plus 5. For the x-intercept, and it's already filled in for us. So for the x-intercept, remember what we want to do is, this is a function g at x, we want to let the function equal 0. So if g at x equals x plus 5, then we let it equal 0, then we can just solve it to find out what x is, right? Here's the problem. There's no value of x that's going to make this equation true. If I put 0 in for x, I just end up with 2/5 equals 0, which is obviously not true. And any number you can think of is not going to work. There is no number that's going to work. So since there's no value of x that makes the equation true, that means there's no x-intercept. How can there be no x-intercept? Well, there can be no x-intercept if there's a horizontal asymptote on the x-axis. So just once again, this graph is going to be something like, well, actually, let's talk about it for a second. It's going to have a vertical asymptote somewhere. Where's the vertical asymptote going to be? What's going to make the denominator equal 0? If x equals -5, the denominator equals 0. So there's going to be a vertical asymptote at -5. And so this graph is going to have a horizontal asymptote at the x-axis again. It's going to look like this, kind of. And so, since it's got a horizontal asymptote on the x-axis, there is no x-intercept. Okay, no problem. For the y-intercept, we simply let x equal 0. Any y-intercept is going to have an x value of 0, so we put 0 into the function. We get 2 over 0 plus 5. The y-intercept is at 2/5. Okay? So that would correspond to this point right here in the graph.